Welcome student in Christchurch Convent Digital Classes, subject Chemistry, class 11th. In this video we will see about Charles law. It is also called temperature volume relationship. Charles and Gay-Lussac performed several experiments on gases independently to improve upon the hot air balloon technology. Their investigation shows that for a fixed mass of a gas at constant pressure, volume of a gas increases on increasing temperature and decreases on cooling. They found that for each degree rise in temperature, volume of gas is increased is by 1 upon 273.15 of the original volume of the gas at 0 degree Celsius. Thus, if volume of the gas at 0 degree Celsius and at T degree centigrades are V0 and Vt respectively, then Vt is equal to V0 plus T upon 273.15 into V0, or if we take V0 common, we'll get Vt is equal to V0 in bracket 1 plus T upon 273.15. Or if we take LCM of equation 5.5, we will get equation 5.6. Vt is equal to V0 in bracket 273.15 plus T upon 273.15. At this stage, we define a new scale of temperature such that T degree Celsius on a new scale is given by T is equal to 273.15 plus T, and 0 degree Celsius will be given by T0 is equal to 273.15. Thus, new temperature scale is called Kelvin temperature scale or absolute temperature scale. Thus, 0 degree Celsius scale is equal to the 273.15 Kelvin at absolute scale. Note that degree sign is not used while writing the temperature in absolute temperature scale, that is in Kelvin scale. Kelvin scale of temperature is also called thermodynamic scale of temperature and is used in all scientific works. Thus, we add 273 more precisely 273.15 to the Celsius temperature to obtain temperature at Kelvin scale. So if we write 273 T is equal to 273.15 plus T, we'll get T0 is equal to 273.15. In the equation 5.16, we obtain the relationship V T is equal to V0 is equal to Tt upon T0, or Vt upon V0 is equal to Tt upon T0. Thus, we can write the general equation as follows: V2 upon V1 is equal to T2 upon T1, or V1 upon T1 is equal to V2 upon T2. Thus, V upon T is constant, that is K2, or V is equal to K2 into T. That means V is proportional to T. So equation 5.10 is the mathematical expression for Charles law, which state that pressure remaining constant, the volume of a fixed mass of a gas is directly proportional to its absolute temperature. Charles found that for all gases at any given pressure, graph of volume versus temperature in Celsius is a straight line, and on extending to zero volume, each line intercepts the temperature axis at minus 273.15 degrees Celsius. Slope of lines obtained at different pressure are different, but at zero volume, all the lines meet the temperature axis at minus 273.5 degree Celsius, as in shown in figure 5.6. You can see the diagram of graph between volume and temperature. Temperature is on the x-axis and volume is on the y-axis. So four graph is shown for four different pressure P1, P2 and P3, where P1 is less than P2 is less than P3 is less than P4. Each line of volume versus temperature is called isobar because it is taken at a constant pressure, drawn at constant pressure. In the next video we'll see about Gay-Lussac law of gaseous volume. It is also called pressure temperature relationship. Pressure in well inflated tires of automobiles is almost constant, but on a hot summer day this increases considerably and tire may burst. If pressure is not adjusted properly during winters, on a cold morning one may find the pressure in the tires of a vehicle decreases considerably. The mathematical relationship between pressure and temperature was given by Joseph Gay-Lussac and is known as Gay-Lussac law. It states that at constant volume, pressure of a fixed amount of gas varies directly with temperature. Mathematically, P is proportional to T, or P upon T is constant. This relationship can be derived from the Boyle's and Charles law. Pressure versus temperature Kelvin graph at constant molar volume is shown in figure 5.7. Each line of this graph is called isochore. So you can see the diagram graph between pressure versus temperature graph, isochore of a gas at constant volume V1, V2, V3 and V4, but V1 is less than V2 is less than V3 is less than V4. The next important law is related to the gas is Avogadro law. It is also called volume amount relationship. In 1811, Italian scientist Amedeo Avogadro tried to combine conclusion of Dalton atomic theory and Gay-Lussac law of combining volume, which is now known as Avogadro law. It states that equal volume of all gases under same condition of temperature and pressure contain equal number of molecules. This means that as long as the temperature and the pressure remain constant, the volume depends upon the number of molecules of the gases, or in other words, the amount of gas. Mathematically, we can write V is proportional to N, where N is the number of moles of gas, or V is equal to K4 into N. The number of molecules in 1 mole of a gas has been determined to be 6.022 into 10 to the power 23, and it is known as Avogadro constant or Avogadro number. You will find that this is the same number which we came across while discussing the definition of a mole in unit 1. Since the volume of a gas is directly proportional to the number of moles of or 1 mole of each gas at standard temperature and pressure, STP will have the same volume. Standard temperature and pressure means 273.15 degree Celsius temperature in Kelvin, or degree Celsius temperature, sorry, 0 degree Celsius. temperature and 1 bar, that is exactly 10 raised to power 5 Pascal pressure. These values approximate freezing temperature of water and atmospheric pressure at sea level. At standard temperature and pressure, a molar volume of an ideal gas or a combination of ideal gases is 22.7.1098 liter per mole. The molar volume of some gases is given in the table 5.2. Molar volume in liters per mole of some gases at 273.15 Kelvin and 1 bar at STP is, you can see in the table, argon 22.37, carbon dioxide 22.54, dinitrogen 22.69, dioxygen, dihydrogen, and ideal gas. The number of moles of a gas can be calculated as follows: N is equal to small m upon capital M, where small m is mass of the gas under investigation and capital M is the molar mass. So V is K4 into M upon M. Or equation can be rearranged as follows: capital M is equal to K4 M upon V. The mass upon volume means density. This equation is given wrong. It should be M is equal to K4. This should be M is equal to K4. This is capital M and this is small m upon volume, and mass upon volume is equal to density. So in this way we'll get equation 5.14. Here d is the density of gas, which is equal to mass upon volume. Now as a gas that follows Boyle's law, Charles' law, and Avogadro law strictly is called an ideal gas. Such a gas is hypothetical. It is only can be assumed, but it is actually cannot be possible because that intermolecular forces are not present between the molecules of an ideal gas. This is the assumption for ideal gas. But intermolecular forces for a gas cannot be zero. Real gases follows these law only under certain specific condition, when forces of interaction are practically negligible. In the next video we'll see about ideal gas equation. Thank you for watching. See you in the next video.